All right, so because we're a little bit behind where I wanted to be, and because I was traveling, and maybe we really didn't have enough time to discuss some things, decided that we'll have an extension on the current problem set, have another week to work on it and get it done. That'll be our last assignment of homework for the semester. That'll be due a week from Wednesday. You should also begin to be thinking about your final project. And as I said, I will be suggesting some potential topics for the term paper. But the project is basically for you to write a review article on a subject of interest to you, in atomic physics, obviously. And as I said, I'll give some suggestions, but I'm fairly open. This is something for you to pursue, something of interest to you. Okay, so we'll talk about that a little bit more in the coming weeks, but you should start mulling it over a bit.
When can you show us the lists?
I'll be getting that together this week. Okay?
Because I've actually not really an idea what I'm...
No worries. I have plenty of suggestions. Okay. Very good. So, let's see. So we've been talking so far in the last week or so, we've been discussing interactions of atoms and electromagnetic fields. We talked about a little bit about absorption and emission from the point of view of Fermi's golden rule, and we talked about in the last week the description of coherent Rabi oscillations when we're driving an atom near to a resonance where we're driving the field, we're driving the atom with a field that is monochromatic or nearly monochromatic. So what we need to do now, we want to make these two pictures eventually come together, these pictures, Fermi's golden rule and the incoherent rate equations that we've discussed a little bit, and this picture of coherent Rabi oscillations. So it's actually quite a involved topic, but let's see if we can just make we're just going to make a little bit of progress on that today. So what we want to discuss is dynamical equations, or dynamics, where we put back the spontaneous emission. So again, what we have been discussing in the last few weeks is a situation in which we are driving the system, say, with some laser frequency that is close to some resonant frequency. And what we have seen is that if we just solve the Schrödinger equation for the evolution of this atom with this time-dependent force, what we find is that we get perfectly coherent oscillations. So this is on resonance. Exactly. Off resonance, of course, what we found was we didn't go all the way to the excited state. and we oscillated at the generalized regimes. Now, of course, this doesn't go on forever. These kinds of oscillations, in principle, are damped out at some point. And that damping can be due to a whole bunch of different physical phenomena. Here we've assumed in this description we had an absolutely single frequency, omega. In principle, that's impossible. We have something close to that. Perhaps we have a highly, highly monochromatic source, but in practice, we never have that. We have something that has a little bit of spread in frequencies. But even if we were able to remove any of the technical imperfections in our system, there's always going to be something fundamentally that damps out these oscillations. And that in this case, would be spontaneous emission. Spontaneous decay fundamentally damps out these oscillations. So how are we going to describe that in the dynamics here? There's something different, as you know, about evolution that's arising due to spontaneous decay compared to the coherent Rabi oscillations. So for example, if we started the system in the excited state and we were to ask if there was no other driving, so let's turn our attention just to the spontaneous emission for a moment. Let's turn off the laser and let's just think about what happens to the system just due to the spontaneous emission. We know in this circumstance the probability to be in the excited state. Let's say initially we started in the excited state and we want to know what is the probability to be in the excited state at a later time. Well, that probability will decay, and that probability will decay exponentially at the spontaneous emission rate, where gamma is 1 over the natural lifetime. It's the Einstein A coefficient. And this evolution over here is irreversible. Unlike this evolution, where wherever we are, we can just go backwards on the curve. Once I get to the ground state, I've decayed. It just stays there. So this kind of evolution doesn't appear naturally as a description of a kind of Schrödinger evolution. As we've discussed earlier, this is a fundamental problem that's shared both in classical physics and quantum physics, in that the fundamental microscopic equations, be they classical or quantum, are time reversal invariant, whereas what we see often in dynamics are dynamics that are not time reversal invariant, where there is an arrow of time kind of going in one direction here, whereas the equations of motion microscopically are not. So there's some effective description, as we know in thermodynamics as well, where we see that dynamics are effectively irreversible, even though they're microscopically reversible, when we have, for example, many degrees of freedom, and the laws of thermodynamics mean that entropy just rules ultimately, and it's just impossible. It takes the time of the universe for the degrees of freedom to recohere and come back and reassemble my broken glass once it shatters on the floor, even though all the information is stored somewhere in all the molecules, when it just, for all intents and purposes, it never happens. And the similar kind, I mean, as I led off this lecture, we can't, there is a formalism with which we can use to try to get from a microscopic description to an effective description which shows irreversibility based on the Schroeder equation, but it's quite involved, and it would take us many weeks to build up that formalism. So we're just going to kind of roll with it a little bit here and get a feeling for how we include this kind of description in quantum mechanics. And for more information, I'll post some notes, and then next semester or next year, I think sometime next year, we'll be teaching quantum optics. For those who are interested, there'll be more opportunities to learn all about it. Well, let's think about this for a moment. If we just had our description of our two-level atom without, so the evolution of the Schrödinger equation would say the probability to be in the excited state at a given time is the square of the probability amplitude to be in the excited state. And for the atom alone, the probability amplitude to be in the excited state, well, this is a stationary state. And so the evolution of that probability amplitude would just be evolution by a phase, because that's the Schrödinger equation. This is a stationary state, and therefore it's an eigenstate. The fact that it's a stationary state is to say that the probability is stationary. However, that's not what we see, even in the absence of any driving. And the reason is, as we've described, that the atom is coupled to the electromagnetic vacuum. So how can we obtain an evolution like this from looking at the square of a probability amplitude? Well, in principle, we can do that. And what do we need to do? Well, we just need to add an imaginary part to the excited state energy. If I add to the excited state an imaginary part, where the imaginary part is proportional to the spontaneous emission rate or the line width of this transition, then if I plug that in, I see that the probability amplitude decays at the rate gamma over 2, and thus the probability decays at the rate gamma. Agreed? if I just square this is a real number, so this thing squares to 1, this absolute magnitude, but this thing squares to e to the minus gamma t. So, an effect of spontaneous emission, or another way of saying this, is the effect of the finite lifetime of the state can be accounted for, at least partially, by adding an imaginary part to the energy eigenvalue. Now, right now that's just phenomenology. I say I can get this the equation that I know to be correct. By doing so, I haven't derived how this comes about, but in fact, this is part of a valid description in the theory of open quantum systems, whereby if I couple a discrete eigenstate of a system so I have this circumstance, which I have the excited state, I have the ground state. This is my atom, say, my two-level atom, but this atom is coupled to the vacuum. So my system, we call this open because there is energy that can move from the system into the reservoir. And that reservoir is thought to be something kind of in the thermodynamic limit, has effective infinite degrees of freedom. And so that energy moves from the system into the reservoir and doesn't come back. That kind of description gives, if this is the state that's coupled to the reservoir, this is a finite lifetime and therefore a finite line width, and that line width can be accounted for by an effective imaginary part. In the same way that in classical physics, if I have a harmonic oscillator with a natural resonance frequency, I can think about that as adding that there's a frequency omega and there's damping, and the damping is an imaginary part. It's like an imaginary part to the natural resonance frequency.
How's this then related to the uncertainty principle? I mean, the time energy?
So there's one, the time energy, sorry, go on.
Is it really the same that you get there? I just wonder.
So the time energy uncertainty principle is a little bit different from other forms of the uncertainty principle, which have to do with non-commuting operators. So I talk about position and momentum, or the x and y components of angular momentum. We know that if we have non-commuting observables, then there is fundamentally relationships by which I cannot determine precisely incompatible observables. The time energy uncertainty principle is more of a rule of thumb. We can look at this as a manifestation of the time energy uncertainty principle, saying that there's a finite lifetime with a lifetime tau, and because there is a finite lifetime, there is therefore some spread in energies which is related to the line width gamma, such that therefore gamma tau is of order 1. You can think about that as a manifestation of a kind of time energy uncertainty principle. That is, because of the fact that I am not, this thing does not have infinite lifetime, it has some finite uncertainty in energy. Personally, I'm not sure that adds any depth to the understanding, other than to say, if it has a finite lifetime, then it has a finite line width. Okay, so it's one way of saying that the line width is inversely proportional to the lifetime.
This is another way. Because you get the same.
Another
Well,
way.
I haven't understood it, but somehow you said that you can see there that because of the finite lifetime you have this way.
I see. Yes, indeed, indeed. I mean, so all right. Yes, indeed. This is we haven't yet come to the description. I haven't derived in any way the fact that there is a finite line width with some kind of spread of energy. We haven't quite gotten there yet. Indeed, you can understand that and interpret that as a kind of time energy uncertainty principle. I was kind of taking that as a given. But we will derive in more detail, maybe on Wednesday, how one arrives from these dynamical equations of finite line width. Okay, so with that said, when I have a finite lifetime, I can add this imaginary part to the excited state. Well, am I done? Does that mean that's all I have to do? All I now have to do in order to understand the dynamics of my atom in the presence of spontaneous emission is to add this imaginary part. Not quite. Why? Well, what about the ground state? How are we going to look at the evolution? We know that when in this problem of the two-level atom, the system decays, and if it's just a two-level atom, if probability leaves the excited state, it must enter the ground state. So the probability of the excited state decays, but the probability of the ground state grows. So you might think, well, I just add the other thing, right? I mean, I'll just go this goes to this plus. In which case, I would say that the ground state but that's not right. I mean, first of all, this blows up. Moreover, it's not that the ground state probability amplitude is growing proportional to itself. It's that it's growing because it's leaving the excited state. So this is not the right equation. I mean, what we really want is that the probability in the ground state is 1 minus the probability in the excited state, which is equal to so that equation is not of this form. I cannot obtain the evolution of the ground state population by just adding in this imaginary part. The ground state is the stable state, and as Cornelius was reminding us, I mean, from this kind of time energy uncertainty perspective, the ground state has infinite lifetime, so there's no effective line width associated with it. It is the excited state that gains this effective line width. So something, we can't just get simply the dynamics of this dissipating system by looking at Schrodinger-like dynamics, but just adding in imaginary parts into our eigenvalues. There's a fundamental reason for that. And the reason is that this evolution, as we've described it, is continuous in time, like the Schrodinger evolution, which I rotated the probability amplitude from the ground state to the excited state. That was our equation for Rabi flopping. This is also a continuous decay. But that's really not also the full phenomena that we know exists, just empirically. Empirically, what we know is that randomly, the excited state jumps into the ground state. That is to say, if I were just, I had a detector out here, here's my atom, and it was like a Geiger counter that clicked when it saw a photon, that would happen at some random time. So we would see some random photon wave packet hit this detector, and at just some random time, it would go click. That time happens within a probability distribution related to the half-life of the atom, or the spontaneous decay rate, but it's a random stochastic process. And this kind of description based on decaying probability amplitudes cannot capture this phenomena that we know exists. It's seen. Now, again, this is a somewhat deep and complex subject. How is it? I mean, we have the full Schrodinger evolution that's describing both the vacuum and the atom, and that's a big, huge unitary matrix, so that in some sense is continuous. When the clicks happen in quantum mechanics remains a mystery. That's something we put in at some level by hand. When does the wave function collapse? When does the click happen? That is not derivable from the Schrodinger equation. However, we have to include it in the description because that's what happens. So, what do we have to do in that circumstance? Well, we now have a kind of, because of this decay, involves some amount, there's something about the decay that also involves stochastic quantum jumps, means that we have to broaden our description of quantum dynamics when there is decay. And what do I mean by this? Well, it means that my dynamics can no longer be tracked by just thinking about the wave function or the state vector. In fact, if I have a stochastic process, then that means that there's some other notion of probability. There's some sense in which there's some probability that the photon decays, and if the photon decays, then the system jumps. And not the photon decays. If the atom decays and emits a photon, then it jumps. If it doesn't, then something else happens. What that means is that I have, in some sense, the wave function has different branches in its evolution. There's the wave function that evolves according to no jumps, and there's a wave function that happens if there's a jump. And they happen with some probability. For example, in a time interval dt, the probability for a jump is little dp, gamma times dt, whereas the probability for no jump is 1 minus that. In that small time interval. So, this fundamental phenomenon that happens leads us to a very important, more general description of quantum states than perhaps you're used to. If you've never seen before, the very important concept of a statistical mixture. So in classical physics, we know that if we have trajectories in phase space, if we don't have complete information about, say, the initial condition, only some statistical description of, with some probability, these are the initial conditions. Or maybe we had a very, very, very well-defined initial condition, but over time, because of the interaction with the air, or what have you, we lose information about the trajectory. Then we would say we have some probability distribution on phase space. Well, the same thing is true quantum mechanically. In quantum mechanically, there's sort of the equivalent of the trajectory is the wave function. But now we sort of lost track of which wave function we're talking about. Because if we don't collect this photon, and we just let the system decay, well then we don't know whether the wave function that we should use is the wave function is associated with the jump, or the wave function associated with no jump. And so we assign, with just classical statistics, this wave function or that wave function. That's a different description from a coherent superposition, where we don't know which eigenstate, but they exist in a quantum superposition. This is more like classical, where I put the chalk between my hands and you've lost information about which hand the chalk is in. So you assign a probability, probably 50-50, because you don't have any information. Yeah, there it is. Now you know. You've collapsed the state, but nonetheless, you have to assign a probability based on what you know about the system.
Isn't the difference just that when we do the thing with the chalk, we expect that it is really one. There is a truth, and there is.
There is a difference indeed, and there is a difference in which we say there is a local realistic value of that chalk in my hand. You just don't know which it is, and so you assign a probability. Versus the chalk is prepared in a coherent superposition, in which case it really, in some sense, isn't one of those things until you correlate it with your measuring device, and then the measuring device. We get into the whole truly difficult questions about quantum measurement. However, the key point here is that this kind of jump, no jump process is just like the chalk. Once the system becomes so big that it loses coherence, then for all intents and purposes, the atom jumped or it didn't. Just like the chalk is in my hand, the right hand or its left, you just don't know which it is. And in that case, what we do is we say that the state is no longer a single density, a single wave function, but we say it is a statistical mixture. Or state vectors. So this is a more general description of a quantum state. And we can specify it. One way of writing it is to say, with some probability p sub j, the state of the system is described by the ket psi j. So this is an ensemble of states. As again, this is not to say that psi is necessarily an eigenstate of energy. It could be in a superposition of excited and ground states. I'm not telling you what the state vector is. I'm just saying that in order to describe this kind of dynamics, I can no longer do so by just keeping track of one wave function or state vector. I need to assign a set of probabilities to different wave functions. And that fundamentally means that I can't describe these dynamics solely by differential equation for a wave vector, unless somehow I kept track of the clicks. If I kept track of the clicks, well then I know which one it is. And then I have a single wave function. Oh, now it's a jump wave function. Oh, no, now it's a no jump wave function. Jump, no. And I just keep doing it. And now, of course, in my erratic behavior there, I was acting somewhat stochastically. So in that way, we would say we can describe this open quantum system by a single Schrodinger equation. But that description is through a so-called stochastic Schrodinger equation. That's a whole nother ball of wax, and that's an interesting subject. However, if I don't keep track of that photon, and I just let the system spontaneously decay, well then I have to deal with this statistical mixture. So, we need to build up a little more formalism in order to discuss that. Let's, for example, suppose I had this kind of surface. I wanted to know what is the expected value of some observable. How would I do it? Well, for each of these wave functions, we know how to calculate the expected value. But I don't know which wave function I have. So I have to ensemble average this over the ensemble of states. Right? I might write this as, in a kind of bastardized notation, by putting a bar over this. This bar is the statistical average as opposed to the quantum ensemble average. Let's look at this in the particular case of the two-level atom. Let's restrict our attention now to the two-level atom. So we know how to calculate this expectation value. So now let me write each of these guys as it's got some amount of ground state and some amount of excited state. And those probability amplitudes could be different for different members of the statistical mixture. All right, let's plug that in. So I'm going to use this notation just because I don't want to keep around all these decorations with I's and J's and so forth. So my expected value of A is equal to, well, I'm just going to plug in this into here. I have CE star averaged plus G star plus G star G plus G star. G. Each one averaged over the ensemble. Now, sorry, the thing that gets averaged, the probability amplitudes are the things that are averaged over the ensemble. Okay, so these things are functions of, depend on which member of the ensemble I have, and then I average this according to that statistical mixture, Pj. Okay? So, what this says is that I can write this expectation value now in terms of the matrix representation of the operator and a matrix, a 2x2 matrix in this case, that represent, whose elements have something to do with this ensemble averaged set of states in the statistical mixture. So I can write this expectation value as the sum over indices alpha and beta, something I'll call rho alpha beta, A beta alpha. Where A beta alpha is just the matrix representation of our observable, and rho alpha beta is a matrix whose matrix elements are here. And this matrix is known as the density matrix. How many of you have studied the density matrix in your quantum mechanics courses before? Okay, good. So you've seen, some of you have seen it. But some of you haven't. So it's an extremely important concept. It's not just about atomic physics. This is generally the description we need to use when we're talking about quantum systems where we need to deal with things that are irreversible. Or, and/or we don't have full description of the state, and we instead must treat it as a statistical mixture of possible states with mixed according to a particular probability distribution. So the density matrix here for our two-level system, or two-level atom, has the matrix representation rho GG, rho EE, rho GE, rho EG, where rho alpha beta is equal to the ensemble average of that product of probability amplitudes. How do we interpret the elements of the density matrix? So, well, we see firstly here the diagonal elements. Say rho alpha alpha. That's equal to this ensemble average of the squares of the probability amplitudes averaged over the statistical mixture. And that is just the probability to be in state alpha, sometimes called the population in alpha. What about the off-diagonal elements? Well, if I look at a case where alpha is not equal to beta, then rho alpha beta is the ensemble average of the amplitude C alpha, the amplitude, the magnitude of the amplitude C beta, times e to the I, the phase of alpha minus the phase of beta. So, what we see here is that the off-diagonal elements here are telling us something about the phase relationship between the different states alpha and beta. And thus, these off-diagonal elements are often referred to as the coherences. Why are they referred to as coherences? They're referred to as coherences because they are the terms that allow us to see quantum interference between the possibilities alpha and beta. Quantum interference is all about phase. So classically, we would just think about populations in the different states, and we'd have rates of populations going back and forth between different states. But quantum mechanically, we allow for the possibility that there are coherences. And the coherences say something about the fact that there is the possibility of quantum interference between the different possibilities, in this case, G and E. This description is true even if we had a single wave function. I could still write down the density matrix. I would just, my ensemble average would not be average at all. I just have a single wave function. So the density matrix is useful there as well. But it's essential if we're going to involve these stochastic jumps in our description.
So I guess it's important to note that the coherence term can be zero because of that, because of the averaging.
That's certainly a good point. We can have a circumstance where as Ben was alluding to, where because of our statistical mixture, the different phases between the different states are so different within the statistical mixture that averaging can cause this to average out to 0, such that the off-diagonal elements in this basis are very small or close to 0, whereas the populations are not. They have to be. We know a few, there are certainly a few, let me see what I have to say here. I'm missing one page here, so I'll just have to wing it. Here we go, right. So, I'm sorry, let me just reiterate that. As this statistical mixture can wash out the coherences, but it will not necessarily maintain and not necessarily wash out the populations. Why? Well, we know a few, we can see from the definition here a few properties of the density matrix. Firstly, how do we normalize the state? Well, if I had a single wave function, we would say that this has to equal 1. But we have a normalized distribution. This equals 1. And this is equal to the sum of the diagonal matrix elements of the density operator. So, in our case, for the two-level atom, it says that the probability to be in the ground state plus the probability to be in the excited state has to sum to 1. So, we can have a circumstance where the coherences wash out, where we have no quantum interference between the possibilities, but we still have population. That's a very different circumstance than we have in closed quantum system dynamics. If I have population in the two states, then I necessarily have coherence in the two states, because that depends. If I didn't have this average, if both of these amplitudes were non-zero, then I would certainly have coherence. The effect of the open quantum system can be to remove coherence between two levels. The other thing we see here, another property that I just want to mention, is that rho, or the matrix, is Hermitian. We see that automatically because we see that by this definition, if I transpose it, that's the same thing as conjugating it. Now, of course, there's a whole bunch of theory of density matrices that we could spend a lot of time discussing, and it's quite interesting, but we're just going to touch some of the surface here to get a little bit of the basic idea. Finally, I guess the last thing I wanted to mention in terms of the properties here is the operator form of rho. So what we just said here was rho was equal to the sum over all the basis vectors, C alpha, C beta, star, beta. So these are the matrix elements, and these are the outer products corresponding to those matrix elements. Okay? So this then is equal to the outer product of this two vectors, ensemble averaged, which is equal to the ensemble average of psi outer product with itself, which is another way of writing I have a statistical mixture of state psi weighted by different probabilities. I take the outer product of that one with itself, and that is a representation of what we call sometimes the density operator. The term density operator and density matrix are synonymous. So this is a basis independent form of the density operator, where I weight by my statistical mixture of wave functions the outer product of psi with itself. Okay, so now what I want to talk about are dynamics. So, let's talk about dynamics with spontaneous emission. Here we are. So, without the quantum jump, so let's consider the free atom, no driving. If I didn't have to worry about the quantum jumps, if the evolution were continuous, well, then we said we can account for the evolution of the probability in the excited state by just saying, well, there is an imaginary part to the eigenvalue, which gives me this decay at the rate gamma over 2. And if I forgot about the quantum jumps, then the ground state would just evolve according to its eigenvalue with no growth or decay. So if I just ignored the quantum jumps, this is what I would see. In which case I would see that the description here is the one we wrote down at the beginning of this lecture. With this description, what do we see the elements of the density matrix doing as a function of time? Well, let me see what we write. Right. So, this is what we had just at the beginning of the lecture. This decays. But what about the coherences? Well, let's look at rho EG, function of time. if I plug that in here, I get CE0, CG0 star e to the minus I, the difference in the energies times e to the minus gamma over 2. This is little. And the ground state would be constant. So this description, ignoring the quantum jumps, shows that the elements of the density matrix, well, this is rho EE. It decays as expected. The population decays at that rate. In addition, a new feature we see is that the effect of spontaneous emission is to decay the coherences. In the absence of spontaneous emission, the coherences would oscillate depending on that energy difference. But in the presence of spontaneous emission, these coherences decay, and they decay at half the rate of the populations. But because we've ignored the quantum jumps, this is constant. So we have to modify our equations appropriately. How do we do that? Well, let's go back now. Let's write down these equations. For these equations now as differential equations. So I plug all that in, I get T star plus complex conjugate and that is equal to minus gamma rho E by dt rho EG this and plugging that in, we get minus I or H bar however, rho GG is equal to so here's the rub. Our evolution of the density matrix, when averaged over all the possible stochastic jumps that could happen, I'm not proving this, I'm just telling you. The effect of that is that I can't just have this continuous differential term. I have an extra term which on average adds a feeding term. This is feeding due to quantum jumps. averaged. Averaged over all possible jumps. Well, in this case, this is 0. So the only term is the feeding term. It's the only way, in the case of the free atom without driving, that the population in the ground state changes. It changes due to the feeding as we take things in the excited state and they jump into the ground state. How big is that feeding term? Well, we know what it is because we know that by normalization, that this has to add to 1. So that means that the time rate of change of the ground state population must equal the negative of the time rate of change of the excited state population in order to maintain normalization. And that therefore is equal to plus. So these equations define the evolution. Of course, this is equal to the conjugate of the other off-diagonal matrix element. Define the evolution of my two-level atom in the absence of driving. What we see in that case is that population in the excited state decays. When it decays, it goes into the ground state. And in addition, coherences oscillate and decay. And they oscillate and decay depending on the difference, the oscillation frequency depending on the Bohr frequency, and the decay rate is gamma over 2. So the density matrix allows us to account for the dissipation due to spontaneous emission. And we must have a density matrix if we're going to account for this feeding term. If we didn't have to worry about the feeding term, well, then we could have done it solely by a Schrodinger-like evolution with an imaginary part to the excited state. And in fact, we will do that. We don't need the density matrix all the time. In fact, quite often, it's much easier, and we often should, not ever forget the fact that we can just work with the probability amplitudes and forget about the complications of the density matrix if we don't have to worry about the feeding. It's much easier. The only reason we have to worry about the density matrix is when we have to worry about the feeding. So for example, if I had a circumstance where there was, say, a third level here that was, say, metastable, and suppose that when this thing decayed, it decayed to that third level. But yet I only accounted for, I was only interested in what's going on in these two levels. This is a situation where, of course, eventually all the probability would go to 0, right? Because I would lose all my population to this third level. But the dynamics of these two levels, excluding this one, is very well described by these two equations. All right. So now we want to put this together. We have the density operator, we have the evolution, including the feeding terms, and now we want to include dissipation and driving. So first, recall evolution of two-level atoms. With driving, no spontaneous emission. In the rotating wave approximation. What did we have? We said that in that case, the ground state, we took the ground state energy to be 0 there, take Eg equal to 0, take the excited state equal to the energy difference. Okay, let's just choose those energies. So in that case, what we found was this is equal to omega over 2, where this is the Rabi frequency. And the excited state we had equal to I minus I omega Eg minus omega L E plus I over 2 omega. That was the Schrodinger equation that we had for the probability amplitudes in the rotating wave approximation, in the rotating frame, where the phase is set to 0. Okay? So now we want to add dissipation. Well, if we ignore the feeding, we know how to do that. If we ignore the feeding due to the spontaneous jumps, we set the excited state goes to the excited state minus I h bar omega over 2. I'm sorry, that's gamma. Okay, so that means here, remember this was minus the detuning. The detuning is the frequency minus the resonance. So the way I've written this here, this is minus the detuning. So in the rotating frame, this means that the detuning goes to the detuning plus I h bar gamma over 2. Right, because the detuning is related to minus the energy in the excited state. Nope, I'm sorry, no h bar here. Okay, so that means that the ground state equation stays the same, but the excited state becomes I delta minus gamma over 2, the excited state plus I omega over 2 ground state. Okay? So as before, let's just forget about the feeding for a moment and just see what these equations tell us. What we see here is this probability amplitude oscillates in the absence of driving, oscillates at the detuning and decays, but because of the driving, we couple the two equations at the Rabi frequency. Let's write down now the evolution of the density matrix. We know how to do it. The way we do it is we use these equations based on the effective Hamiltonian with an imaginary part to the eigenvalue, and then by hand add in the feeding terms. Okay? That accounts for the stochastic jumps. So let's do it. the excited state, there's no feeding term, so I could just do this. Plus complex conjugate. Right? So that is equal to minus gamma rho E plus I omega over 2 CG CE star. So that's rho GE. And then the complex conjugate, that's an I rho EG. All right? This is a new, before when we didn't have the driving, we just had decay, but now we have driving. Similarly, rho EG is equal to CG BT G star plus the conjugate so then we have for this guy is equal to I delta minus gamma over 2 rho EG plus I omega over 2 CG, CG star, that's rho GG, and then I have to do the conjugate of this guy, which is minus I blah 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 minus and these are the two equations we need because this, according to the fact that the density matrix is Hermitian, means that the other off-diagonal element is just a conjugate, and we obtain the terms related to feeding simply by just insisting that this is a trace-preserving map, or another way of saying that is that population is conserved. So these equations define the dynamics of my two-level atom coupled to the laser field, which drives Rabi oscillations, and the vacuum, which gives rise to spontaneous emission. We often call these equations the master equation, which comes from a much broader term relating to non-equilibrium statistical physics, where we think of the evolution of a probability distribution outside of equilibrium, and the equation that governs that in classical statistical physics is called the master equation. We adopted that term in quantum mechanics to talk about that more generally as the equation that determines the evolution of the density operator. Let me just conclude. We'll talk about this much more on Wednesday, but let me just conclude by saying, what did the dynamics mean here? Well, we started this discussion at the beginning of this lecture by saying in the absence of damping, we had, if we were on resonance, we had unit oscillation, Rabi oscillations. And those equations, or this solution, follows from this equation if I set gamma to 0. Not obvious maybe, but that's the solution. If I include damping, what's going to happen? Well, what I get are damped Rabi oscillations. I no longer have perfectly everlasting, forever oscillations, but the oscillations are damped. And the damping rate depends on gamma. Now, of course, I've shown here a kind of underdamped oscillation where gamma was smaller than, and somewhat smaller than the Rabi frequency. But when the Rabi frequency is small compared to the rate of spontaneous emission, like say in an alkalized is 5 megahertz, if you put on 100 megahertz, 100 kilohertz Rabi frequency, well then what you would find instead was something that was more overdamped. In which case I would see no oscillations at all. I would just see a steady rise to whatever the steady state solution of population would be. And it's in the regime where the oscillations are damped, and the oscillations have gone away after the transients have gone. That is the regime and I mean by transients, in this case, oscillations at the Rabi frequency or generalized Rabi frequency. After the transients decay, that is the regime of Fermi's golden rule. That is the regime in which, as Ben alluded to, coherences are gone, they've decayed, and instead all I have is population that is changing with some detailed balance, ultimately giving rise to steady state. So that's what we're going to discuss next time, how to connect, look at the solutions at some limits in steady state of these master equations of motion to understand better the dynamics of two-level driven systems in the presence of spontaneous emission and the relationship ultimately to Fermi's golden rule. All right? Action here, whereas the equations of motion microscopically are not. So there's some effective description, as we know in thermodynamics as well, where we see that dynamics are effectively irreversible, even though they're microscopically reversible when we have, for example, many degrees of freedom, and the laws of thermodynamics mean that entropy just rules ultimately. It's just impossible. It takes the time of the universe for the degrees of freedom to cohere and come back and reassemble my broken glass once it shatters on the floor, even though all the information is stored somewhere in all the molecules, when it just, for all intents and purposes, it never happens. And the similar kind, I mean, as I led off this lecture, there is a formalism with which we can use to try to get from a microscopic description to an effective description which shows irreversibility based on this shorter equation. But it's quite involved, and it would take us many weeks to build up that formalism. So we're just going to kind of roll with it a little bit here and get a feeling for how we include this kind of description in quantum mechanics. And for more information, I'll post some notes, and then next semester or next year, I think sometime next year, we'll be teaching quantum optics for those who are interested. There'll be more opportunities to learn all about it. Well, let's think about this for a moment. If we just had our description of our two-level atom without, in the last week, the description of coherent Rabi oscillations when we're driving an atom near to a resonance, where we're driving the field, we're driving the atom with a field that is monochromatic, or nearly monochromatic. So what we need to do now, we want to make these two pictures eventually come together, these pictures, Fermi golden rule, and the incoherent rate equations that we've discussed a little bit, and this picture of coherent Rabi oscillations. So it's actually quite a involved topic, but let's see if we can just make we're just going to make a little bit of progress on that today. So what we want to discuss is dynamical equations, or dynamics where we put back the spontaneous emission. So again, what we have been discussing in the last few weeks is a situation in which we are driving the system, say, with some laser frequency that is close to some resonant frequency. And what we have seen is that if we just solve the Schrödinger equation for the evolution of this atom with this time-dependent force, what we find is that we get perfectly. All right, so because we're a little bit behind where I wanted to be, and because I was traveling, and we really didn't have enough time to discuss some things, decided that we'll have an extension on the current problem set, have another week to work on it, and get it done. That'll be our last assignment of homework for the semester. That'll be due a week from Wednesday. You should also begin to be thinking about your final project. And as I said, I will be suggesting some potential topics for the term paper. But the project is basically for you to write a review article on a subject of interest to you, in atomic physics, obviously. And as I said, I'll give some suggestions, but I'm fairly open. This is something for you to pursue, something of interest to you. Okay, so we'll talk about that a little bit more in the coming weeks, but you should start mulling it over a bit.
When can you show us the lists?
I'll be getting that together this week. Okay?
Because I've actually not really an idea what I'm...
No worries. I have plenty of suggestions. Okay. Very good. So, let's see. So we've been talking so far in the last week or so, we've been discussing interactions of atoms and electromagnetic fields. We talked about a little bit about absorption and emission from the point of view of Fermi's golden rule, and we talked about there was no other driving let's turn our attention just to the spontaneous emission for a moment. Let's turn off the laser and let's just think about what happens to the system just due to the spontaneous emission. We know in this circumstance the probability to be in the excited state. Let's say initially we started in the excited state and we want to know what is the probability to be in the excited state at a later time. Well, that probability will decay, and that probability will decay exponentially at the spontaneous emission rate, where gamma is 1 over the natural lifetime. It's the Einstein A coefficient. And this evolution over here is irreversible. Unlike this evolution, where wherever we are, we can just go backwards on the curve. Once it gets to the ground state, I've decayed. It just stays there. So this kind of evolution doesn't appear naturally as a description of a kind of Schrödinger evolution. As we've discussed earlier, this is a fundamental problem that's shared both in classical physics and quantum physics, in that the fundamental microscopic equations, be they classical or quantum, are time reversal invariant, whereas what we see often in dynamics are dynamics that are not time reversal invariant, where there is an arrow of time kind of going in one direction, coherent oscillations. So this is on resonance. Exactly. Off resonance, of course, what we found was we didn't go all the way to the excited state, and we oscillated at the generalized frequency. Now, of course, this doesn't go on forever. These kinds of oscillations, in principle, are damped out at some point. And that damping can be due to a whole bunch of different physical phenomena. Here we've assumed in this description we had an absolutely single frequency, omega. In principle, that's impossible. We have something close to that. Perhaps we have a highly, highly monochromatic source, but in practice, we never have that. We have something that has a little bit of spreading frequencies. But even if we were able to remove any of the technical imperfections in our system, there's always going to be something fundamentally that damps out these oscillations. And that in this case, would be spontaneous emission. Spontaneous decay fundamentally damps out these oscillations. So how are we going to describe that in the dynamics here? There's something different, as you know, about evolution that's arising due to spontaneous decay compared to the coherent Rabi oscillations. So for example, if we started the system in the excited state and we were to ask